Okay, good evening, everyone. So, thank you for those joinings. And yeah, for those who are watching the recorded lecture, please remember to record your attendance using this QR code. Okay, so yeah, I hope the internet connection is fine. I tested, actually it was okay. So yeah, I hope those attended the online lecture also yeah, you can hear me clearly, I hope. Okay, so after you have recorded the attendance, so yeah, this is lecture number 10. So I hope you are aware that from this lecture onwards, so all the topics will be covered in your final exam. Okay, so there will be 5 lecture, week number 10, 11, 12, 13, and 14. Okay, so the lecture for 5 weeks will be included in your final exam. So yeah, I hope you can pay even more attention. And in this 5 week, we are going to cover the topic that is even more at once. Okay, so so far we have covered the 4 basic methods for data analysis. So we have clusterings, which actually I would say is very important in engineering, okay, or in system engineering. And then the second one is on association rules. So we don't see a lot of this kind of application in engineering, but we see this the use of association rules mostly in computer science or information science. Okay, so mostly in the minings, the data minings, and so on, the information minings. And then we have what we call the regressions. Okay, the linear regressions, that's where we calculate linear regressions and logistic regressions. It's a very fundamental method, but we see a lot of applications using linear regressions. Okay, and in fact, what we are going to cover today on the time series analysis is actually related to regressions. Okay, is related to regressions. And then the last one, we have classifications, which we cover last week. And yeah, again, classification is a very popular or very useful data analysis. We basically see this classification in many applications in engineering. Okay, so in image processing, when we talk about image processing, that include object recognitions, um, object detections. So we use this object recognition, object detection in many different domains. Okay, yeah, in for example, yesterday someone asked me about autonomous driving. Okay, in autonomous driving, in fault detections, fault detections, or the fault classifications in manufacturings, and then in what else, um in communication system. Okay, we detect different type of security attack. Okay, so or abnormally in the uh in the traffics, in the network traffic conditions. Okay, so yeah, there are a lot of different applications for classifications. Okay, let me see, someone text me. Is it okay? Sorry. Can you let me scan the QR code? Okay, maybe later you watch the recording to scan the QR code. Okay, yeah. So yeah, so today's we are going to cover a more advanced data analysis method that is on time series analysis. I would say that this is even one step more difficult than um if let's say I relate this to linear regressions. So this is a much more complicated versions of linear regressions. Okay, so later we will see how. Okay, and yeah, if you look at the schedule, so we also have next week on natural language processing, or and on text processing that is related to language. It's also another more challenging task, but I'm sure you're aware that text processing or natural language processing, or we have a new name we call the large language models. Okay, it's a very important task nowadays. Okay, and then after that we'll talk about using deep neural networks, okay, using deep learning for similar data analysis, but we focus on big data where, you know, where the data is huge, okay, that involve high dimensionality, and that means many features, okay, a huge number of features. Okay, so actually in time series analysis, okay, we are trying to models the structure of the of an observations of a features, okay, of a characteristic over time. So that's why the difference between linear regressions and time series analysis is that, you know, the data is recorded over time. So it's basically the same parameter, we record it over time. Okay. And in this chapter, so we are studying a time series where they have equally spaced value of time. Okay. Yeah, equally spaced. That means, for examples, we will record, okay, we will record some parameters every day, daily, okay, at 12 p.m. for example, every day. So that's why the interval is fixed. Okay. On linear regressions, basically we do not have these requirements. Okay, for linear regression, we do not have these requirements. We can record the data at any times. Okay, yeah. So that is the main difference. And a time series, against, you know, we can denote, okay, we can represent using these very simple equations, linear equations, y equal to a plus bx. Okay, so again, x is the independence variables or the input, and y is the dependence variable or the output. Okay, and where a and b are the constant. So yeah, we try to formulate, or we try to train a model to fit into these equations, So again, they are limited to only equally spaced time series of, and the thing about time series analysis here is, you know, the input parameter x, okay, the input parameter is only one, okay, it's only one variable. So we are trying to find the relationship between the output and also the input, and only one input, okay, only one input. So what is the goal of this time series analysis? We want to identify or we want to train a model. Okay, we want to train a model that can represent the time series. Okay, and then we can use this model to forecast, okay, or to predict the future value. Okay, another very important characteristic of this time series analysis is, you know, the prediction is just over a short period of time. Okay, so that means we can predict what happens, for example, tomorrow, okay, or maybe 1 hour ahead, one hour from now. Okay, that means we are predicting what will happen in the next hour, okay, or the next day. So usually is over a short period of time. Okay, so we cannot predict something that is very very far away. That means after maybe, you know, a few years and so on, we cannot do that using time series analysis. Okay, so most of the time we are just predicting the near future. Okay, we are predicting the near future. So yeah, so that's why these are some of the applications. So basically time series analysis, the most important is in finance. Okay, it's in finance. It's related to the stock market analysis. So yeah, you know, this is very, very important for finance. Okay, stock market analysis, you know, so that can make someone rich within a day, or, you know, within a few minutes or seconds. So it's a very important task for them, you know. So yeah, they analyze the historical stock price, and then they identify the trend and the pattern, and they try to predict, you know, the future price. So if your prediction is very accurate, yeah, you can become millionaire or billionaire, you know, within seconds. Okay, so yeah, it's help trader or investor in making what we call the informed decision. Informed decisions mean, you know, it's not a random guess. Okay, it's not a random guess. It's some decision based on some predictions. Okay, some sound predictions. Okay, but of course, you know, again, it's a predictions. It's not 100% accurate. So that's why yeah, so that's why when you invest in stock market is quite is that is risk, okay, and the risk is quite high, okay. So yeah, and but of course, you know, those in finance, you know, those we call that what we call that you know, those people working in finance, working in banking, okay, so they will use this information to assess the rates, the risk, and then to plan their strategy, okay, to plan their trading strategy. So yeah, you see, last few years there are also a few lecturer in my department, in the electrical engineering departments, you know, so they offer a lot of project that is related to, you know, stock market predictions. So I believe they invest a lot in the stock market. Okay, so yeah, and now we are using uh all these deep learning models. They are using all these deep learning models. Okay, but so far I think they are not very successful. Okay, why? Because they are still working in the departments. So I believe if they have a very good models, and then if they have make a lot of money, maybe they will not become lecturer anymore. So far I still see them around, so I think they have not get a very good models. Okay, so yeah, maybe you can try. Okay, you can try. This can be your project as well, okay, your research project as well, because although it's finance, but it's related to deep learnings, you know, data analysis. So yeah, we can do as well. Okay, so yeah, the first one is not so related to engineering, but we still apply the knowledge, okay, the deep learnings, the data analytics techniques. Okay, so the second one, okay, so yeah, it's the energy consumption in demand forecasting. So basically, you analyze the historical energy consumption pattern and forecast the future demand. Okay, so yeah, I think energy consumption is especially important in the four season countries. Okay, because for example, during summer or during winter, okay, you will see a drastic increase in the demands for the energy. Okay, so that's why, and I believe that, you know, this kind of demands, okay, uh will increase over time. Okay, will increase over time. Okay, so yeah, so that is where yeah, we can use time series analysis, okay, to do the predictions. Okay, for example, yeah, for example, I heard that, you know, in I think, yeah, how to say, early this year, okay, the winter is very cold. So in country like Japan, Korea, you know, China, okay, so the temperature is very low. Okay, they have a lot of snow and so on, very cold temperature. So yeah, so and I think it's kind of like, maybe it's like a trend that is becoming colder and colder. Okay, so let's see, about 20 years ago, I stayed in Japan for 4 years. 4 years. Okay, in Japan there's no snow at all. Okay, I didn't see any snow at all, but this year I heard that, you know, even Tokyo got a lot of snow. Okay, I think it's the most in the past 40 years. So that's why there is a trend. Okay, so the trend may not be keep increasing or keep decreasing, but you know, somehow they have a trend. So maybe using a very good models, okay, and we study all the data for the past, you know, 30, 40 years, okay, maybe we can make a very good prediction models. Okay, and you can imagine that the temperature or the weather definitely have impact to the energy consumptions. Okay, definitely got impact to the energy consumption. Okay, like I said, especially summer, if very hot, okay, so yeah, okay, so you will switch on the air cons, you know, then more energy consumption. If winter is very cold, you need the heater. Okay, also very high energy consumptions. Okay, either you use electricity or you use gas. Okay, but we can see that. Okay, so yeah, if we can predict the trends, you know, we can plan accordingly, we can manage the resources in a more efficient way. Okay, or do we want to plan for some infrastructure upgrade, you know, more power generation, more power station, and so on. Okay, so all this can be done using time series analysis. Okay, so in Internet of Things, in sensor data analysis, so we enable real-time monitorings and anomaly detections. Okay, predictive maintenance, and then optimization of the process. Okay, so we use IoT in manufacturing, we use IoT in transportations, in healthcare, in agricultures, yeah, and in smart city, smart home, so everywhere. So if we have the data, if we, usually IoT is installed with or with sensors. So there will be a lot of sensor data, then yeah, you can do a lot of analysis. Okay, so for example, even now, most of our houses, okay, our residential houses, or I think even commercial building, are installed with smart meter. Okay, so yeah, so this smart meter will collect the informations, okay, about the electricity utilization in the house. Okay, so at what time you use the most. Okay, and then I believe they also know what type of appliance, yeah, that we are using based on our utilization trend and so on. Yeah, so because for example air cons, with fan, so that is definitely a difference pattern in the um energy utilizations. So from there, we can obtain a lot of information. We can obtain a lot of information by doing this time series analysis. So yeah, on environmental and monitorings and climate analysis. So like I think I mentioned many times, I have students, okay, working on the air quality, outdoor air quality predictions, mainly focus on the PM 2.5 and PM 10. Okay, so PM is the particulate matter. So it's like, those pollutants, how small are they, So yeah, based on yeah, the historical data, we can predict. Okay, we can predict. And then yeah, since we are predicting the outdoor, we are predicting the city air quality. Okay, so that can help in the urban planning, so the planning of the city, so that's we want to reduce the pollutions, we want to maintain the air quality at a healthy level. Okay, and so on. So yeah, all this yeah, we need very accurate or very fast time series analysis. Okay, so yeah, we also include, we can predict the weather patterns, and also about, and then using environmental sensors. So yeah, nowadays we deploy more and more environmental sensor, so that we can predict, some of the event that will happen. Okay, so yeah, I believe there's some research they are trying to install sensor to capture, those even very small signal, and hopefully they can have some early detection of earthquakes, for example. Of course not in Malaysia, okay, in Japan, in Taiwan. Okay, so I think even also in China, so there are some earthquake there. So yeah, by installing some sensor, hopefully, we can kind of like have some early detections. Okay, yeah, or we can kind of like predict whether the earthquakes will happen or not. But according to what I know, previously we cannot predict earthquakes. So when it's happened, it happens, you cannot predict. So but we don't know if we can install sensor, very sensitive sensor, maybe we can capture some very small signal, maybe I do. Okay, yeah, so that that we can have some early detections. So maybe, if the prediction is just 1 minute before the earthquake, actually that make a lot of difference. Okay, actually that make a lot of difference. Okay, so yeah, so I have not looked into the all this natural disaster topic recently. So I believe this time series analysis definitely can help into this the natural disaster preventions and also mitigations. So because when it comes to natural disaster, we mostly focus on two parts. Of course, one is on preventions. Another one is on mitigation. Mitigation is after it happens, how we can, recover, okay, or how can we can rescue the victim and so on very fast. Okay, so yeah, it is always focused on these two parts. So I believe time series analysis can play some important role. Okay, in this kind of events. Okay, so yeah, on traffic and transportation analysis, I think this is also related to smart, sorry, related to smart transportation system. Okay, so yeah, we can analyze the traffic pattern and so on. Okay, so yeah, so it's help in the traffic management, the route optimization, and so on. Okay, and then on healthcare and patients monitoring. Okay, so yeah, so yeah, there are a lot of research. There are a lot of research. Okay, they talk about early detection of heart attack. Okay, and yeah, especially a heart attack. So by having some putting some variable or some devices. Okay, so we will keep monitorings on the patient's vital. That's what we call those pulse rate, and then blood pressures, maybe breathing as well. So yeah, we can kind of like detect abnormality. Okay, and then yeah, we can have some early detections of some disease, especially like say heart attacks. Okay, or even not that serious, not those disease, this is also a very good monitoring system for healthcare. Okay, because I think nowadays, I think most of us are wearing wearable already, so we don't wear the conventional watch, so we watch the we wear the wearable. So yeah, many data are recorded, how many hours we sleep, how good the quality of our sleep. Okay, and then how active are us, how many steps we walk every day, do we do exercise or not, so all this, if we do put in a time series analysis, so we have a very good informations about a person. Okay, yeah, so from there, but so far, we don't see that the hospital or the doctor are using this kind of data in their diagnosis. Okay, but I believe in the near future, all these informations are important to them. Okay, are important to them. So it will not replace them, definitely, but I believe it will provide very essential informations about an individual, okay, related to their health. Okay, and of course, if they are not very well, can also have some informations about the progress. Okay, do we call that a progress? Okay, so yeah, the progressions of their disease. Okay, so yeah, I think some of the disease, we know that they will progress very slowly, but they will definitely progress. Okay, for example, dementia, for example, Alzheimer, Parkinson, all this. Actually, there are a lot of research, they focus on this type of disease. Okay, that will progress over time. Okay, that will progress over time. So that's why, again, this is a time series analysis. Okay, so in time, so for this many example that I give you, okay, so some of these tasks required a much more complicated models. Okay, a much more complicated AI models. So but what we are going to cover in this lecture is the basic one. Okay, the simplest one. So that is why now we see a lot of deep learning models. Okay, deep learning models, because this deep learning model can take in more input, can take in more features, and then yeah, and then analyze the non-linearity, and then have very good feature extractions, and also attention mechanism. Okay, to identify the features. Okay, so yeah, all this may not be able to be solved using the method that we are going to cover today, but definitely there are some more advanced time series models that we can use for this type of task. Okay, what is important in time series analysis, and how this time series analysis is different or similar to the linear regressions. Okay, similar or different with the linear regressions. Okay, so first we are looking for this time series analysis, is we are looking at the trend. Okay, we are looking at the trend which refer to a long-term movements or the long-term changes. Okay, or the long-term variations of the time series. Okay, so yeah, so generally the most basic one, we are observing whether the trend is increasing or decreasing. But in most of the time in time series analysis, you will see fluctuations. You will see a highly fluctuated data or series. Okay, but even it's highly fluctuated, we can still see some trend. Okay, we can still see some trend in the time series. So that's why one of the tasks, okay, of this time series is we identify the trend. Okay, so it's one of the components. Okay, and what is difference between time series and the linear regression is, is the seasonality. Okay, so another component is called seasonality, because yeah, I believe you understand season. Okay, so some country they have 4 seasons. Okay, so that's why even the season not really refer to the 4 season. Okay, the season only means that there's a periodic fluctuations. There's a periodic fluctuations. So the season can be like really the 4 season, like every 3 months, or the season can be 1 week, Monday to Sunday, and then repeat Monday to Sunday. Okay, the seasonality can also be 1 day, 24 hours. What, some 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 things, okay, will change and repeat every day. Okay, we repeat every day. It can be daily, it can be maybe monthly, it can be yearly, or it can be really seasonally. Okay, every season. Okay, so yeah, so that's why it's important for us to identify the seasonal components, the seasonality components. Okay, so yeah, so that's why when we look at the data, we still have to do some data exploratory. Okay, again, go back to our chapter 4, right? So it's still very important for us to understand the data. Okay, yeah, in time series analysis. So we may want to look at whether the data demonstrate some seasonality. Okay, some periodic fluctuations that we can see. Okay, okay, the next one is called cyclic. Okay, so this is also periodic fluctuations. Okay, but it's not fixed with season. Okay, it's not fixed with season. So I would say it's a more random kind of periodic fluctuations. Okay, so the seasonality is kind of like a fixed periodic fluctuation, like I say, every day, every month, every year, or every season. Okay, a cyclic is basically more randoms, more random. Maybe for this, maybe for this kind of data. Okay, so it's every 2 months. Okay, and then after that it will be like uh 3 months. Okay, so it's not fixed. Okay, it's not fixed. Okay, also in time series, another component is called a random components, or we call the noise. Okay, so we call the noise because you see, even for example, we know that some country they have 4 seasons. Okay, but for example, the winter, they may start at slightly different time. Okay, yeah, I think one example, very good example, is the sakura blooming in Japan. Okay, the sakura blooming in Japan, we know that it happens around March, April, or sometime late April, or sometime even if colder, that will be somewhere in May. Okay, so we know that it's going to happen around that time, but it's not fixed. It's not like every year 1st of April you will have sakura. You don't have that. I think same as weather. Okay, same as weather. So there are some random components that should be included so that our time series is more generalized. Okay, it's more generalized. So that's why in other words, it's not overfit. Okay, it's not overfit. So if a model is overfit, that means if you train like that, that means it will predict, okay, every year 1st of April you will have sakura. So that is not accurate. So we have to include some, because all this random component is a noise. When we hear about noise, that is not good. Noise that's not good. But actually in AI, we need noise. Okay, we need noise. Noise actually make the model more robust. Okay, not overfit, more robust, which is good. Okay, so yeah, actually I changed the slide a little bit. Okay, so if you download the slide before today, so yeah, I hope you will download again from the spectrums. Okay, because just now when I go through the slide, I add on a few diagram lah. Okay, so yeah, so you can see this is quite interesting. Okay, recently, you know, recently the gold price actually increased drastically. Okay, so this is what my friend told me. Okay, I don't buy gold also, so I got no money to buy gold. Okay, so and you can see that, you know, the gold price actually increased following an increasing trend. Okay, so even though we see fluctuations, we see even here, you know, we see small fluctuations, but what we can see is increase over time. So that's why if you buy in around 1980s, okay, let's say, you know, let's say it's about 400. I think this is $400. $400 usually is what, 1 gram? I don't know. I really don't know gold, if you know it. So is it, let's say this is 400 per gram. Let's say that, okay? So if you sell the gold now, it becomes 2,200 or maybe around 2,000 per gram. So it's 5 times already. Okay, so generally we see a trend in the increasing. So that is from 1980s to 2020, 40 years. So that's why you should buy now. And then in 40 years, you know, in about 2060, I think you can predict that it will be another, you know, maybe 5 times or even more. Okay, so that's why you should start buy gold now. Okay, yeah, when you are after 40 years, when you're old, yeah, I think the price will be double or triple. Okay, so yeah, better than any currency. Okay, so this is where you will see trend. Okay, you will see trend. But you don't really see seasonality here. You don't see really seasonality. But maybe if you look into carefully, okay, because if we just look, you know, if we just look like this or observe like this, we may miss some of the trend, you know, we may miss some of the informations. But who knows, if you use a very good model um to check this, right? Maybe they'll notice, oh, every 5 years it will drop. Every 5 years actually it will drop. There are still some seasonality there. Every 5 years it will drop, it will drop. Okay, but overall we still see an increase, but we still see every 5 years it will drop. Okay, maybe, you know, just example. This is not something that we can just see. You know, we can just look at this and we know. If we can look at this, we know that we don't need AI models. Okay, so that's why we need AI models to help us to extract the information. Then it will be able to do the predictions. It will be able to do the predictions. Okay, yeah. So yeah, this is another examples. You know, it's the average monthly. Okay, so it's the average monthly temperature in the UK. So from 2015 to 2023. Okay, so I believe in this diagram, the graph actually they give is a bar graph. Okay, so if they give a line chart, if you plot this, the line chart, I believe you can see some seasonality. Okay, definitely you can see some seasonality. So this is what, this is July. Okay, July, August. So you can see almost every year, July or August, you know, or around July, August, the temperature will be the highest. Okay, yeah, 2023 is a little bit different. June is the hottest. Okay, it's the highest temperature. Okay, but overall, you know, it's around this, okay. So this, you can see a seasonality. You can see a seasonality of about 12 months. Okay, of about 12 months. That means every 12 months you will see some pattern. Okay, for example, this is among the lowest. Yeah, every 12 months you will see that they are among the lowest. Okay, so in this kind of data you see seasonality. Okay, and maybe, you know, but I don't see the trend now, because you can see it's very much quite the same. Okay, yeah, but maybe, you know, with global warming you will still see that, you know, although there's a seasonality, but maybe the hottest month the temperature will keep increasing. Then you will see trend and seasonality. Okay, in this one you see only trend. Yeah, I cannot see seasonality, but not necessarily there's no. Okay, so I by you know, by a simple exploratory or observations, I don't see the seasonality. But for this one, it's very obvious there is seasonality. Okay, so yeah. So again, the first step is we want to observe the trend. Okay, it's important. So that is related to our data exploratory. Okay, yeah. So yeah, this is the introductions of time series analysis. Okay, so the method that we are going to use, is called ARIMA models. Okay, ARIMA. So I also have a case study at the back. Okay, so there are 3 sessions in today in this lecture. Okay, so okay, let me take a 5 minutes break to rest a while. Okay, then we continue with this one because this is quite long. Okay, so let's take a 5 minutes break. Okay, so for those who are watching the recorded lecture, you can fast forward about 5 minutes. Okay, so we continue at 7:40. Okay, let's continue. Okay, so let's continue and look at a very simple models. Okay, a very simple model is called ARIMA models. So actually, the term ARIMA, actually we are using three techniques here. Okay, one is AR, one is MA, and then another one is the the integrated. Okay, so we will see the three methods. Okay, the three mechanism. Okay, then we combine, they become these models. Okay, so this method is based on what is called a Box-Jenkins models. So it's a mathematical model designed to forecast data, okay, range based on inputs from a specific time series. Okay, and what we are going to focus again in this chapter is only one input. Okay, it's only one input. So it's involved the following steps. So these are the steps. So condition data and select a models. So we need to make decisions on the parameters. Okay, the parameters of the models. Okay, so how to do that? We need to look at the data. We need to look at the data. We may need to modify the data. They talk condition the data, the data conditioning. So and then we select a model. And I think this is also related to what we say about data exploratory. Okay, so when we condition the data, yeah, then you also look at the trend and or the seasonality in the time series. Okay, and then after that we examine the remaining time series and determine a suitable models. So later we'll go through the step. After that we will estimate the model parameters. So again here, we can only estimate the models, and then after that we evaluate how good is the models. And then if not good enough, we come back, to improve the model and test again. So it's still an iteration step. Okay, so it's still an iteration. So you can see, okay, you will evaluate the models and then return to step one. Okay, and then do again until you obtain a model that is good enough. Okay, so that is good enough. So yeah, so we basically based on the Box-Jenkins methods, okay, to apply ARIMA. So again, ARIMA stands for autoregressive. So this is AR. Autoregressive is one method. Okay, and another method is called moving average, MA. Okay, moving average, and integrated. When you integrate these two methods, and actually there's another method here. When you do the integrations, we call the differencing. Okay, we call the differencing or detrending. Later we will see. Okay, so basically there are three techniques or three mechanisms that we combine together to make these models, and then we train these models, and then we use this model to forecast to predict or to forecast the future, the near future. Okay, remember it's near, within the short time. If too long time, cannot. Okay, yeah. So someone text me, if you already record the attendance now, you do not need to record the attendance tomorrow. Okay, so record the attendance only one time. Okay, so the first step. Okay, so the first step, okay, we need to remove any trend or seasonality in the time series. Okay, so we want to remove the trend and remove the seasonality. That means if you have a keep increasing trend, we want to improve, we want to remove this keep increasing trend. Okay, if we have the seasonality, we will remove the seasonality. So that will be our first step. Okay, yeah. So after that we will look at the autoregressions and also the moving average. We apply these two, okay, later. Okay, and it's very important, okay, very important for this method. Okay, we use for stationary time series. If you study probability and randoms, random process or random variables, I believe you know what is a stationary process. Okay, a stationary process, and in this case we call a stationary time series. Okay, what is a stationary process or a stationary time series? Okay, so there are a few characteristics. So the first one, okay, the expected value or the means, the average, the mean is a constant. Okay, it's a constant for all value of time, for all value of time. So you can see here, is the average constant over time? No, right? So you can see for this one, if you calculate the average, it's somewhere here. If this you calculate the average, is somewhere here. If this you calculate average, yeah, this part very much the average will be the same. And then from here you can see if you calculate the average, it keep increasing already. Okay, or maybe they decrease a bit, but overall you will see that the average keep increasing. So the average or the means, the means is not a constant. It's not a constant. So that's why this one we cannot use ARIMA model unless we remove the trend. Okay, we remove the trend so that it will become constant, that it will fulfill the first requirement. Later we will talk about how we do the detrending. That means we remove the trend. That's later. Okay, so and then the variance must be finite. Okay, the variance is not infinite, it must be a finite value. Okay, and what is important here, the covariance. Okay, the covariance of yt and yt plus hash only depends on the value of hash. Okay, so what is yt and what is yt plus hash? Okay, so that is the output. That is the output at different time. Okay, so that is the output of different times. Sorry, give me a minute. Let me install my pen. Drawing pad. I forgot to install this. If I install this. Okay, now I cannot install. Okay, so you can see, I don't have extra USB. So you can see this is YT. YT, for example, if T is now, okay, YT is the output now. Okay, YT plus hash, that means is the value of the output hash step ahead in the future, hash step ahead in the future. If hash is zero, that means there's yt and yt lah. That means itself. Okay, so mean the relationship of the output with itself. Okay, if your hash is equal to 1, that will be yt and yt plus 1. Okay, let's say if every step is 1 minute, right? Let's say every step is 1 minute. So that will be, if t is equal to 1, so that is the value of the output at minute number 1. And then y1 plus 1, 2. Okay, if hash is 1, so that will be the output at minute number 2. Okay, if hash equal to 2, that is t plus 2, right? That's t plus 2. So that will be the output after 2 minutes. Okay, yeah, that's, sorry, minute number 1, minute number 2, minute number 3. So that is the relationship between the output now and the output after 2 minutes. That means minute number 1 and minute number 3. Okay, if it's minute lah, okay, every step is minute. So that's why this covariance actually talk about the relationship between the current output and the future output. Okay, and this covariance value, this relationship only depends on hash. It doesn't depend on t. Okay, so that means between yt and yt plus 2 and y4 and then y4 plus 2, the covariance will be the same. Okay, so the covariance will be the same. So yeah, that is what is yt and yt plus 2. Okay, yeah. Yeah. Okay, so yeah, I hope you can follow this. Okay, give me a minute. I think I still need. Okay, yeah, can you still hear me? Okay, right? I'm still connected, right? Can you just make sure you can hear me? Hello.
Yes, doctor.
Okay, thank you. Okay, so yeah, okay, because okay, so I cannot. Where's my draw? Okay, so that's why if this is my YT, okay, so this is YT plus 2, okay, T plus 2. For example, if my hash is equal to 0, okay, so yeah, let's say this my T is 1, okay, my T T is 0, okay, so T plus 2 will be this will Y0, this is Y2. So if I calculate these correlations and then I compare with, for example, this is Y4, this is Y6, you can see this hash is also equal to 2. This hash is also equal to 2. Okay, and the correlation between Y4 and Y6, okay, the correlations between Y0 and Y2 will be equal to Y4 and Y6. Okay, because it depends only on the value of hash. Okay, so yeah, Y is the output. That means output at 0, this is output at 2, output at 4, output at 6. So if we look at the correlation between output at 0 and 2 and output at 4 and 6, it will be the same because it depends on hash. So similarly, if my hash is 3, okay, if my hash is 3, so this is Y0, this is Y3, and then let's say I have another one, Y4, and then plus 3 is Y7, okay? So you can see the correlations between, the covariance between Y0 and Y3 and the covariance between Y4 and Y7 will be the same because the hash is equal to 3 for both. Okay, so similar for hash equal to 4 and so on. Okay, so yeah, if you fulfill this requirement, and this requirement, then yes, it is a stationary time series. Then we can apply the ARIMA model. Okay, so the ARIMA models. Okay, and you just have to take notes of one thing. If hash is equal to 0, we are looking at the covariance of YT and YT. Okay, so the covariance of YT and YT actually is equal to the variance. Okay, it's equal to the variance, which is this one. So actually for stationary, there's only 2 rules. Okay, actually this one is included here. Okay, so it's included here, but yeah, but the textbook put into 3 different requirements, so we just follow lah. Okay, yeah, so yeah, just a little bit revision on what is covariance. Okay, if the two variables, okay, for example, again, here we are talking about the input and the output are independent. That means they don't depend on each other. Okay, then their covariance is 0. Okay, sorry, not X and Y, is YT and YT plus hash. Okay, so if the covariance of YT and YT plus hash is close to 0, then actually YT and YT plus hash are independent. Okay, are independent. What does it mean? It means that, you know, this output at YT plus hash kind of like doesn't depend on YT. The correlation is very weak. Okay, the relationship is very weak. So that's why that is, you know, in time series, then we will not need to use this to predict this one because they are not really related. Okay, yeah. So you can imagine, you know, for example, your weight now, okay? Your weight now, okay? You are 50 kg. You are 50 kg. Okay? So last month you are 49 kg. Okay? This month you are 50 kg. Okay? Maybe before this you are 47 kg. Okay? So you see, you can use, you can see, you know, this is 1 month, this is 1 month. You can see it's somehow still related. Okay, maybe you use this tree, you can predict your weight next month. Okay, yeah, if you follow this trend, you will know what is your weight next month. But let's say, you know, this is your weight 100 kg. This is your weight in year 2000. Okay, wow, year 2000 also, yeah, 24 years. Oh, this I think before you were born. Okay, this before you were born. Okay, for example, in 2010. Okay, so for example, in 2010, 10 years ago. Okay, 14 years ago, you are 100 kg. So I believe that, you know, your weight next month, your weight, sorry, the pen is very, so your weight next month, okay, your weight next month definitely doesn't depend on your weight about 14 years ago, right? So that's why if you calculate, what happens? Okay, if you calculate the covariance of next month, okay, and the covariance in 2010, this will be very close to zero. This will be very close to zero. Okay, if you calculate the covariance of last month, April, and this month, May, you will see that the covariance will be very high. Okay, so it's either it's a positive covariance or a negative covariance. Okay, a positive covariance means it keep increasing. Okay, when it come from April to May to June, your weight will be keep increasing. It's a positive covariance. Okay, a negative covariance means, you know, when the month increase, your weight will decrease. Okay, so that is a negative covariance. So yeah, that is the relationship about covariance. And I think I also give a kind of like a good example, okay, uh, for you to see the correlations. Okay, the hash is how far apart, Like I say, you know, last month compared to about 10 years or 14 years ago. Okay, so you can see the covariance with 14 years ago will be very small, close to zero. But the covariance of now and last month maybe is very close to a very large positive value. Okay, because it will be highly correlated. Okay, yeah. So if for a stationary time series, okay, we calculate the covariance using this method. Okay, we will minus with the means. Okay, so again, this is the means. Okay, so this is the means. Okay, yeah. So this is covariance. Okay, so it's important for us to know the covariance. Okay, yeah. So now we look at how we do the data exploratory. Okay, how we do the data exploratory. For example, this is your time series. Okay, so this is your, oh, I didn't do animations. Okay, never mind. You can see this is your time series. Okay, so first, okay, we must determine whether this is a stationary time series or not. How do we see? We kind of like calculate, we kind of like look at what is the means value. Actually, if you do a little bit of statistic analysis, the very basic, you know, what we study in week number 5, some statistic analysis, we can see that the means is almost constant. Okay, the mean is almost constant around zero, regardless of time. So this fulfill the first requirements. The means or the expected value is constant, okay, for all value of t, and the value is equal to 0. And then we look at the distribution in this part, you know, larger than the means and smaller than the means. Okay, so it's almost equal. Okay, it's almost even distributed, you know, larger and smaller. So that's why here we can kind of like predict, okay, not predict lah, we can observe, okay, the variance is constant, okay, or is almost constant over time. Okay, you can see the distributions is almost even. Okay, yeah, of course we cannot say it's exactly constant, but because this is just by observations. Okay, by observations, is fulfill the second requirement. But from here we cannot see the covariance. Okay, so that is why the first step, okay, of course the first step is you do these observations lah. Okay, so this is the second step. Okay, we have to plot what we call a ACF, okay, autocorrelation functions. How do we calculate the autocorrelation functions? We use these equations. Okay, so the x-axis is hash. Okay, so we start hash equal to 0, hash equal to 1, hash equal to 2, 3, 4, 5, and so on. Okay, we look at different value of hash, and then we plot the covariance. Okay, so you can see if hash is equal to 0, so it's covariance 0 divided by covariance 0. So you always get at 0, the value is equal to 1. Okay, so the autocorrelation function at 0 is always equal to 1. Okay, and then this is covariance 1 over covariance 0. And remember, covariance 0 is the variance. Okay, it's the variance. So if you plot the graph, basically you will observe that the SCF is kind of like keep decreasing. Okay, the autocorrelation function will keep decreasing. Why? I think just now I already explained. Okay, so for example, this is now. Okay, this is now. So that's why your autocorrelation is always 1, because now you relate to now is definitely equal to 1. It's very related because it's now. Okay, so for example, you compare 1 year ago, okay, this year and last year, I believe you can imagine that it's still highly related. Okay, it's not very independent. Okay, and then you compare separate by 2 years, separate by 3 years, separate by 4 years, 5 years, and so on. I believe after you compare now with 25 years ago, you will see that the covariance will be very small, right? Will be very small. So that is why. But it's not always. But basically, they follow a trend of decreasing. They follow the trend of decreasing. Okay. And then, yeah, I mean, from here we will see. Okay, if the value is close to 1, that means they are highly correlated. The covariance is high. They are highly correlated. They are not independent. So that's why if it's related, of course, I want to use the data for my predictions. I want to use the data in my time series. So that's why the question is how many I want to include. Yeah, I think I need data from last year because it's related. I think I can use the data 2 years ago. It's also very, if you look at the functions, it's also very related. Maybe 3 years ago, also quite related. I want to use last year, 2 years ago, 3 years ago, maybe 4 years ago, and so on. Okay, so how to decide on that? We look at some confidence level. For example, I say, okay, if the autocorrelation function is more than 0.6, okay, so it's about 60%, then I will consider. Okay, so let's say if set our threshold at 0.6, okay, so I zoom in a little bit. So if let's say we set the threshold at 0.6, so you can see, yeah, 1, 2, 3, 4, 5, 6, 7, 8. Okay, 9 is already less than 0.68. That means I will use the data for the past, let's say it's last 8 years, okay, last 8 years to predict what happens next. Okay, to predict what happen next. Okay, so it depends on the threshold. Okay, if you set your threshold higher, for example, if you set your threshold to 0.8, for example, okay, if you use 0.8, then you will only use 1 and 2. Okay, you will only use 1 and 2 because 3 is already less than 0.8. Okay, so it depends on the threshold that you set. Okay, depends on the threshold that you set. So this parameter we call the lag. Okay, we call the lag. Okay, so yeah, this is lag number 8. Okay, this is lag number 8. Okay, so if your lag is number 8, I will create a auto regression models. I will create an auto regression model of order 8. Okay, of order 8. Later we will see what is the auto regression models. Okay, but now if based on the auto correlation functions and based on the threshold, I will do 60% confidence level. I will create a auto regression models of order 8. If I increase to 80% just now, if I increase to 80%, I will use order 2. Okay, I will use order 2. So this is how we determine the order of the auto regressions model or the AR models. So again, if you come back to ARIMA, okay, so this is the AR model, okay, the auto-regressive model, okay, or sometimes I call auto-regressions, okay. So what is an auto-regressive models? Okay, what is an auto-regressive model? So this is an auto-regressive model. So you can see it's a time series. It's a time series, but it's not different features. It's not different features, but it is the previous output. Okay, the previous output. It depends on how many order. Okay, if this is 8, right? So this is 8 and t minus 8. Okay, yeah, if we follow order of 8. So then, yeah, that will be your equations for AR. We put ARP. So in this P, if P is 8, so this is the equations. Okay, yeah. So you can see this is a linear regressions. It's like a linear regression equations, but I do not take a different input, but I take the value of the output for the last 8. Okay, the last 8. 1, 2, you know, this is the current one. This is the previous, the second, the you know, two step before until 8 step before. Okay, so this is the auto. Sorry. Okay, so this is the auto regressive models. Okay, ARP. P is the order. Okay, and what are these? Okay, what are these parameters? So this delta, this small delta is a constant. Okay, is a constant to compensate the average, to compensate the means. Okay, if the mean is not 0, if the mean is not 0, then there will be a value here to make it, okay, to make the average back to 0. Okay, so this is a constant for non-zero center time series. For this case, you can see the mean is 0, so it's centered at 0. If that is the case, your delta, okay, your delta will be equal to 0. Okay, if it's a 0 center, then it will be equal to 0. Okay, and then all this similar to linear regression, all these you know, phi 1, phi 2 until phi p are just constant. These are the previous input, the previous output. Okay, the value of the time series at the previous lah. Okay, the previous value. Okay, and this one must not be 0 because you are of order p. Okay, if this is equal to 0, then it's order p minus 1 already. It's not order p already. So that's why this value cannot be 0. Okay, and this part again is the error. Is the error or is the noise? Okay, is the error or is the noise? And again, we model this using white Gaussian noise. Okay, using white Gaussian noise. Okay, so that's why again, I believe you can see this is also a linear regression, a linear equations. Okay, it's a linear equations of p prior values. Okay, up to t minus p. So yeah, this is how, after that, you know, we will fit this model. We will fit this model using the database. Okay, using the data set. Okay, so but we are not doing the fittings method lah. We are not doing the fittings step by step. Okay, so basically we will program and let the computer to do it lah. Okay, yeah, yeah. So we want to see, okay, we want to see a little bit deeper, okay, whether do I really need, for example, in this case, right, this is AR8. You can see if you have AR8, these equations will take the last 8 value. Okay, so actually the question is it really necessary? Okay, is it really necessary for us to take up to so many, you know, past value? Why? Because we know that, okay, even for AR1 model, for AR1 models, so this is AR1 models, right? It's only one. We know that if even we are using AR1 models, this YT minus 1 can be substituted, it become this one, right? Because if YT depends on YT minus 1, then yt minus 1 depends on yt minus 2, right? So that's why if we write these equations, it can become like this. And this equation, I can further substitute yt minus 2 equal to phi 3 yt minus 3 plus epsilon t minus 2, right? So that's why you can see, even is yt, we can relate to yt minus 2 or y3 minus 3, yt minus 4, and so on, okay? And so on. So that's why they still have impact, okay? So all this, even we are taking only one level, but this depends on this one. So that's why yt minus 2 also have impact on yt, okay? So that's why, that is why we need to know, is it really necessary? What is the impact of, for example, in this case, what is the impact of this at 8? H equal to 8 to current. What is it to current? So in order to do that, okay, we plot what is called partial autocorrelation functions. Okay, partial autocorrelation functions. So again, this is the equations how we calculate the partial autocorrelation functions. Basically, we are calculating the correlations between the current and also the future. Okay, that is H step behind. Okay, no, sorry, H step before. Okay, H step before. We want to find the correlation, so that's what we call the partial autocorrelations. Okay, but we remove, okay, we remove the impact for everything in between. That means we are looking at t, and for example this t plus h, without considering the impact of all the value in between. We just consider this and this, okay, these two. Okay, so this is a partial autocorrelation functions. Okay, so don't worry, you are just using an equation to calculate, and we don't need to calculate. So if we plot this PSCF, okay, so a few observations that we can see. So we can see that, the PSCF, some of the value will drop quite drastically. Okay, so that's why we can see basically some observations. The PSCF at 1 actually is equal to SCF at 1. Okay, SCF as 1, it will be very correlated. And if we look at the others, we can see that after lag 2, so this is 1, this is 2. So after lag 2, the ACF, the PSCF will become very small. It's all become kind of like uncorrelated. So in fact, that's why we say that only lag 2 is sufficient. Okay, because what happened after lag 2, after H equal to 2, the PSCF is reduced drastically, sharply. Okay, so that's why actually, we do not need, even from here, it say that, up to lag 8, okay, is still correlated, is still related. But all this correlation actually is not important if we look at the partial. Okay, so actually it's not really important anymore. Okay, because the how to say, the impact, right, will be bring forward to here. Okay, so that's why by having lag 1 and lag 2 actually already sufficient. So that's why we do not really look at SCF. In fact, we look at PSCF to decide on the order of the autoregressive models. Okay, we look at the PSCF instead of the SCF to determine the order. Okay, yeah. So yeah, when we calculate SCF and PSCF, the value, the correlations can be positive or negative value. So that's why most of the time we don't look at the sign, either it's positive or negative. We just look at the absolute value. Okay, we just look at the absolute value. Okay, yeah. Okay, so this is the AR models. Yeah, next is the MV models. Okay, MA model, sorry. Okay, MA models. Okay, it's the moving average model. The moving average models, basically, we are kind of like modeling the error. So the moving average models can be represented with another linear equations. another linear equations. So we model YT based on the error up to Q order. So in this, the Q and the P, right, just now is MARP, okay? So this is MAQ. So it's different order, okay? So we may have different order for the autoregressive and also different order for the average model, okay? It depends which one, okay? So, yeah. So yeah, this equation, I believe I don't need to explain much. So again, it's a linear equations. Okay. So the value of the time series is a linear combination of the current white noise terms and then the prior Q. Okay, the prior Q, how many Q? Okay, white noise term. Okay, yeah. Why? Because if there is some noise that happens, even long time ago, the impact may still carry until now. Okay, for example, 2 years ago, suddenly you enjoy eating, you eat a lot, your weight increased a lot, or your cholesterol level increased a lot, your cholesterol level. Okay, so even after 2 years, the impact will still have, you still have the impact after 2 years. you know maybe your cholesterol, maybe you will control your diet, but your cholesterol may still be high. Okay, so maybe after 4 years later, yeah, maybe if you control nicely, maybe your cholesterol will drop further or your weight will drop further. After 6 years, yeah, the impact will be less and less, but there's still some impact there, similar to the autoregressive model. Okay, so it's the similar models. Okay, so yeah, so again, in the same case, it actually is the same step. Okay, you have the data. For example, I simulate these equations. I simulate this equation to obtain the data. Okay, and then I plot the SCF. You can see that this is 0, 1, 2, 3. Okay, 1, 2, 3. The SCF still have some value, but after that, no more already. Okay, so that means the impact is only up to 3. After that, after the 4th year, no impact already. So in this case, I would decide on using the Q equal to 3. Okay, yeah, so the Q equal to 3. Okay, so yeah, so therefore when you select the value of Q, you have to make sure that the autocorrelations, the SCF, should be close to 0. Okay, for any lag that is greater than 3. So for example, okay, then Q. For example, if your Q is 3, so you can see all this SCF is very, very small. It's close to 0. So then the Q is 3. Okay, so yeah, for the AR, basically we use the PSCF. For the MA, it's sufficient to use SCF, but you can always also use PSCF. It doesn't stop you. Okay, yeah, if let's say the SCF, the lag is very big, you may want to look at PSCF to see whether you can reduce the order further or not, because after all, we don't want the models to be very large. Okay, we don't want the model will be to be very large. It's just nice to accept to obtain a good models. Okay, a good models that is sufficient. Okay, so that's why whether you want to use AR model or MA models, actually you can use just AR model or you can just use MA models, but actually they propose to combine AR and MA models. So that's why they have this ARMA, or we call AMA models. Okay, so P and Q. So remember, P is the order for AR, Q is the order for MA. So we just combine the two equations. So this is AR, this is PQ. Pula. This is AR, this is MA. Okay, AR, MA. So we combine the model and then we train the models. Okay, yeah. So so again, if you want to use these models, the time series must be stationary. Okay, must be stationary. If it does not fulfill the stationary criteria, you need to do some adjustment. That means some pre-processing to the data. Okay, some pre-processing to the data. So yeah, how can we do the pre-processing? Okay, how can we see remove, okay, how do we do the pre-processing, or how do we remove the trend? Okay, we call that detrending. Okay, detrendings. Okay, so we can use the same models similar to the regressions analysis. Okay, so for example, you can take square, or you can take, you can take the square of the the previous output and so on, to make it constant. Okay, to make it constant means, and then the autocorrelation depends on only Hirsch. Okay, so the criteria is there. Okay, but if cannot, because detrending we already do in the linear regressions. So in here in time series, they prefer to use something called differencing. Okay, they prefer to use something called differencing. Differencing is very easy. Okay, so instead of they plot the YT, they plot the output, they plot the difference. The difference, that means YT minus YT minus 1. Okay, so if you do one time, this is one time differencing, and you see whether you get what you want or not. So you can see, if let's say I have this data, right? I do one time differencing. So from here, you can see, I think I already achieved a stationary. You can see the means is always is around 0. And then you can see the variance is almost there. And after that, you can, sorry, where is it? Yeah, after that, you should also plot the SCF. Okay, you should also plot the SCF to look at the correlations. Okay, if after one time differencing, you already achieve stationary, then okay, then you will continue with the ARMA. Okay, if not, you can also difference again. Okay, you can apply higher order differencing. Okay, that means you take DT minus, you difference dt. So it's the difference of the difference. Okay, so this is the second order differencing. If not, then you will do higher and higher order. But most of the times, is very high orders differencing is not recommended lah. It's not recommended. So mostly it's just first order one times or two times. If really cannot, you may consider a different method. Okay, so yeah, this ARMA with differencing we call ARIMA. Okay, the integrated ARIMA. Okay, ARIMA models. Okay, so again, over differencing you should be avoid, because that will that is not necessary. Okay, that will increase your variance. Oh, I still have a lot. Okay. Yeah. Okay, let me finish this one. Then I will take a break. Then we go for the case study. The case study should be short. Yeah, so next we talk about season. Okay, so seasonality is quite easy. Okay, seasonality is quite easy. If you see a season, what you do is you will apply, can still use the ARIMA models, but before that you will remove the seasonality first. Okay, you will remove the seasonality. Okay, so how you remove the seasonality? You still apply the ARIMA models on the seasonal, considers the seasonality. After that, you consider ARIMA without the seasonality. Okay, so that's why this we call seasonal auto-regressive integrated moving average, or SARIMA. Actually, you just add a S here. Okay, so yeah, it's a seasonal ARIMA. Okay, it's a seasonal ARIMA. So it's just the ARIMA, add this one to remove seasonality, where S denote the seasonal period. So typical value of the S is, for example, if weekly is 52, if monthly is 12, and then if daily is 7 lah. Okay, yeah, so and etc. If seasonal, maybe is 3. Okay, but different country, they may have a different time for the season, so it's not necessarily 3. Okay, so it depends. Okay, and then P is the number of terms in the AR model across the S period. Okay, so that's why this is the same ARIMA, but this is the P and the Q and the D, the differencing for the seasonal part. And this small letter PTQ is for the overall, okay? It's for the overall. So it's kind of like two ARIMA models, okay? It's kind of like two ARIMA models. Okay, so yeah, this should be very fast. So there are some others methods, for example, autoregressive moving average with exogenous input. I don't know what is it. Okay, I didn't use it. And then you may use spectra analysis. This is especially useful in speech the speech signal recognitions, because the speech is also a type of time series. Okay, a video also a type of time series. In fact, natural language processing, our language is also kind of like a time series. Okay, and we also have this generalized autoregressive. Okay, and some other models. There are quite a few models. Okay, Kalman filter, I think for some of you who are working on the signal processing, you are very familiar with Kalman filter. Okay, and then vector ARIMA. So it's just a different versions of the ARIMA. Okay, yep. So after that, we will use the trained models. We'll use the trained models to do some forecasting or predictions. Okay, so yeah, the prediction. One way to do the predictions. Yeah. Where is it? Yeah, the simplest one is you just plot the graph lah. Okay, you just plot the graph, then you can see how much difference between the predicted value or the forecast value and the actual value. This is for you to do testing lah. Okay, yeah. And yeah, you can use some other parameter, quantitative parameter. I think last week we already talked about mean square error, mean absolute error, mean average predictions error. Okay, root mean square error. Okay, and some other statistical tests. Okay, and some other statistical tests and some parameter, for example the R square. Okay, so these are all the parameters that we can use for predictions. So yeah, these are all the steps for ARIMA. So you may want to ask me, after you decide on the PQ and the D, you know how to use the D. Okay, so the D is just differencing. Okay, after you have the D, so you have PQ. How do you do that? I skip the part because that part is just mathematics. Okay, you will take the data from the data set, put in the equations, and then calculate the error, and then go back, do again, and then until your maybe if you use a mean square error. Okay, so until your mean square error is below some value, is below some threshold, then you will stop the training. Okay, so it's just a normal iteration based training process. So that's why I will not cover here. It's quite similar to linear regressions. Okay, it's quite similar to linear regressions. Okay, I will take another 5 minutes break. Okay, so maybe yeah, easy to calculate, 7 minutes. So I will continue at 8:35. Okay, let my voice rest a while. So we just have a short case study after that. Okay, so we come back at 8:35. Okay, so let's continue. So yeah, it's short sessions. I think 25 minutes I can finish. So yeah, we look at one case study. So we have learned the method. So this case study will show us a more systematic way how to apply ARIMA models. Okay, so that's why the case study is like this. So for a large country, it's just any country lah. So the monthly gasoline productions measure in million of barrels have been obtained for the past 20 years. So this is the data of 20 years. So 20 divided by 12, so it's 240 months, okay? So that's why I think this is months. So that's why it's supposed to have a 200 up to 240 months, okay, of data. And this is the average of every month, okay? The average of every month. So a market research firm required some short-term gasoline production forecast to assess the petroleum's industry ability to deliver future gasoline supply. Okay, and then they will look at the effect of the price. Okay, so yeah, basically based on these 20 years of data, they are kind of want to predict the futures. Okay, the futures these gasoline productions. Okay, yeah. So that's why when you look at when you have the data set, so first I think we do the data exploratory. We plot the data, we plot a very simple, you know, line graph, okay, to look at the productions over the last 20 years every month. Okay, so that's why after that, I think first thing, if we want to apply ARIMA models, we want to check whether it's stationary or not. So that's why the question is this, okay, is this stationary? Okay, so obviously if you look at the average, if you check the average over time, right? If you check the average over time, okay, it's not a constant, okay? It's not a constant. So if the data, okay, so if the data is not stationary, so what is the next step? What is the next step? Okay, what is the next step? So the next step is you apply differencing. Okay, so you apply differencing. So how you apply differencing? You will take the data of the current one minus the previous one. So remember, the differencing means you just calculate the difference. Okay, you just calculate the difference. So you take the current one minus the previous one, and then another one is minus the previous one. Then you will be able to plot the differencing. Okay, so after that, yeah, you look at this. So this is the difference lah. So this is the difference. This is the time. Okay, so you know, if you use Python, the Python will do everything for you. So so that's why you don't have to worry how to obtain this. Okay, yeah, you can look at the code. Okay, but yeah, in this case study, let's say after you do the differencing, you get something like this. Okay, so the question again is the same question. Is this stationary? Is it already stationary? Okay, so it's look more stationary. Okay, it look more stationary. Okay, you have a kind of like a constant average, and then the variance is quite constant as well. Okay, so yeah, so the question is it sufficient? Is it sufficient? Okay, so yeah, from here I think it's quite sufficient. You get a zero means, and then the variance, okay, is kind of like a constant. Okay, so I just assume one times differencing is sufficient. Okay, one time differencing is sufficient. So you know, when you do in real data analytics, you may apply the differencing another times. You may apply the differencing another time and to compare. Okay, so differencing time 1 and differencing time 2. Yeah, what is the difference? Will this be even more stationary? Okay, even more stationary. Then you may use the second differencing. Okay, but in this case study, I see this is already quite sufficient. So that's why I will go to the next step. What is the next step? Next step is I will need to look at, you know, is there any seasonal data? Okay, is there any seasonality? How to look at seasonality? We look at SCF. We plot SCF. Okay, we plot the auto correlation functions, and then we use 95% significance level. Okay, we use 95% significant level. Okay, so based on here, you can see that, you know, the ACF decrease is kind of like decrease, but every 12 months, the ACF will increase back, you know, will increase back. All those over period of time is decreasing, but after 12 months, it suddenly become important. So this indicates a seasonals, okay, a seasonality of 12 months. Okay, yeah, you can see one at 0, you know, after 12 months, after 24, so this is 12. So this have a seasonality of 12 months. Okay, yeah, and yeah, this is 95% confidence. So only the value larger than this 95% confidence level is counted. Okay, it's counted. So if we have seasonality, we have to take care of seasonality first. Okay, so we have to take care of the seasonality first. So that's why what happens now next is we plot the partial SCF. Okay, we plot the partial SCF. Okay, and then we see, okay, at here, after lag 12, is still significant, but at 24, 36, 48, it become quite small already, or less than the 95% confidence significant level. Okay, even for partial SCF, we look for 95% significant level. Okay, for at 12 is still more than this 95% threshold, but at 24, 36, 48 is already not very significant already. Okay, so not very significant already. So that's why the lag equal to 12. Is the lag equal to 12? Are we going to use AR12? That is the questions. Okay, so in fact, it's not. In fact, we don't use that. Okay, in fact, if we look at here, okay, if we remove, after we remove the, actually the seasonality is not very important. Okay, yeah, after the second year, the third year, and the fourth year. So that's why the seasonality is only important after 1 year. Okay, or after 12 months. Okay, so after 12 months. So if my seasonality is 12, so this is actually equal to 1. So that's why I use a seasonal AR1. Okay, I use a seasonal. So this is seasonal 12 month AR1. Okay, AR1 means one cycle of the season. Okay, the second cycle and the third and the fourth cycle of the season is not important already. Okay, that means, you know, I only depends on the data last year. I do not depends on the data 2 years, 3 years, or 4 years ago. Okay, yeah, so that is how I obtain this part 10012. Okay, yeah, and why there's a 1 here, remember at the beginning I do one-time differencing. Okay, yeah, I do one-time differencing. This is the original models, this is for the seasonal. Okay, so that's why the auto regression is 12 months. Okay, and most of the times, you know, we will address the seasonal first, then only we address this the original ARIMA. Okay, so we try to use this model, we try to use this 100 model, and then we train it. We train this 100 model. So let's say, you know, after we train, we got these coefficients, and the error is this one. Okay, yeah. So go back to your AR. Go back to your AR. Where's my AR? AR. So that's why you can see it's just one term only. So you only have and this is 0 because the average is 0. So you only have you only have this YT, this part, and this part. Okay, after you train the model, you will get this phi 1 and also the error epsilon t. Okay, so that's why this parameter and this parameter, after you train the models, you get this value and this value. Where is it? Yeah, you get this value and the error is this one. Okay, so yeah, maybe I should copy this. Okay, yeah, so it's just one model. Okay, so it's just this one. Okay, so yeah, this is this one. Okay, so and this is the error. Okay, so that's why yeah, this is the AR1 models. Okay, yeah. Okay, so this is the AR1 model. So you already estimate the value. Okay, this is by training. Okay, by training using the data set. Okay, using the data set. So yeah, we will not do it manually. It's not possible to do it manually. Okay, so yeah, after that we will evaluate these models. Okay, we will evaluate these models. Okay, actually if I write like this will be better. Okay, if I write like this will be better. So this will become, so this is 0.8335 plus 0.0324. Okay, so yeah, that's how I got this model. So this is the AR models. Okay, after that I will evaluate. Okay, so I will evaluate the residues. Okay, so that means I will evaluate the models. After I have this one, I will fit the residue of the fitting. Okay, after I fitted the model, I will look at the residues. That means the difference. Okay, so and then after that I plot the ACR. I plot the SCF again. Okay, so you can see here, if you plot the SCF again, you only remain lag 1. Okay, so this is 0, this is lag 1. Although it's a negative value, doesn't matter. Okay, the magnitudes, you know, the absolute value is still larger than the 95% confidence. Okay, so what we do is, again, we plot the partial SCF. We plot the partial SCF, and this they make the scale smaller. So this is still the 95. So that's why I have 1, 2, 3, 4. I have 4. Okay, so again, what is the moving average? What is the MA, the order, or the Q lah? What is the Q that I want to use? Okay, if we follow here, it will be 1, 2, 3, 4. Okay, so this is about 9, also larger, but just a little bit. So that's why, do we want to use MA4? Okay, do we want to use MA4? But again, you know, we try to avoid using a large value of Q. That means, you know, we don't want to use the very long time ago historical data, because we don't want to overfit it. Okay, we don't want to overfit. So that's why the selection here is still 1. Okay, is still 1. Okay, so instead of 4, I take only the first one. Why? You can see from 1 to 2, is a drastic decrease. Okay, it's a drastic decrease. But from 2 to 3 to 4 is smaller. So okay, it's smaller. So that's why in this case study they choose 1. But let's say if you choose 2, 3, or 4, is it wrong? It will not wrong. Okay, it will not wrong. You may get a even more accurate model. You will get an even more accurate models, but your model may also be overfitting. That means your model only suitable to be used for this case. You know, when in future, in a longer future, maybe your model is not so suitable because your model is so overfit with the current situations. Okay, so your model may not be able to continue to use after some times. Okay, because your model is so overfit. Okay, so that's why there's this kind of design, there's no fixed answer. So again, there's no fixed answer. So yeah, based on here, you know, the textbook say, you know, from 1 to 2, a drastic decrease, but from 2 to 3 to 4 is just a small one. And I don't want to use a large value of Q, because I don't want to overfit my model. So that's why he select 1. He select 1. So that's why now is yes, anything? Okay. So it's a MA 1. Okay, and AR is also 1. AR is here, MA is here. So again, after that, I will do another time of training. Then I obtain this one. So these are the parameter. So again, you just substitute this one into the ARIMA equations lah. So the ARIMA, this one. Okay, you just substitute. No, not. Yeah, right. This is AR. This is MI, right? Yeah, AR, MI. Okay, so you will get this. Okay, after you train. Okay, so yeah, both are significant. And again, we look at the residues again. Okay, after we fit the models, we compare with our test data. We look at the data again, and I zoom in a little bit. Oops. So you can see, except at 0, all the other are smaller than the confidence level. Okay, are within the confidence level, or smaller, not within. Okay, so same for this one. My confidence level is here. Actually, they just make the scale larger. Okay, I didn't increase the confidence level. It's still 95% significant level. So you can see all the different lag, all are smaller than this threshold. So that's why then, is a good enough model. Okay, it's a good enough model because the residues mean the difference. Okay, that means the difference is very small already. Okay, so it's a good models. So basically, even I use only this MA1, and then AR1, seasonal is 12. Okay, differencing one time, good already. Okay, so already good. Okay, so the next step is we will use this model. We'll use this model that we train to forecast the gasoline production for the next 12 months. So again, we zoom in. We look at here. Okay, so yeah, so this is the actual data. So it's the actual data. Sorry, this is the predictions. So this is the predictions, the predicted data. So this and this one is the 95% confidence level. That means plus minus 5, like the plus minus 5%. Okay, so yeah, the prediction is here. Okay, so after that, if you have your data, okay, so you will compare how accurate is your data. Okay, so let's say if, yeah, this is your, let's say if this is your real data. Okay, not good on my pen. So then you can calculate how good is your prediction. Okay, you can calculate how good is your predictions. Yeah. Okay, so yeah, so this is one example of case study. I hope you get familiar with the step. Okay, you just need to get familiar with the step. You don't have to worry about how to calculate the coefficient and so on. Okay, so we will not do the calculations. If later you want to see how the models and are trained, because you just need to write the Python code and then they will give you the answer. So yeah, you please look at the 2 example. So again, I will not run the code because there's no meaning. I just run the code and show the result. So I will leave the Python code to you. And again, I hope you will run this because I spent some time to make the output similar to what we study. So I believe the code will help you to understand better. Okay, so yeah, the last slide. Okay, the last slide is very briefly. Okay, this is also some homework that I want you to do. Okay, some homework that I want you to do. So I want you to look at the advantages and or we talk about the pro and cons, or the strength and limitation of these ARIMA models. Okay, so yeah, one advantage of the ARIMA model is simple. Okay, it's simple, and then it's just based on historical time data. Okay, it's just based on the historical time series data. Okay, so that is good. It's a simple model. Okay, it's a simple model, and quite often the predictions is quite accurate. Okay, it's quite accurate. Okay, but the disadvantage is that the disadvantage is also is this. Okay, it's too simple. Okay, so the model does not provide an indication of on what variables or what other variables that will affect the outcome, because you only consider one variables. Okay, one variables, and this time series analysis is should only be used for short-term forecasting. Okay, that means you are predicting the near future. You cannot predict very far away. You cannot predict something that's 1 year later. Okay, you can only predict what happened tomorrow. Okay, and tomorrow you can predict what happened the day after tomorrow, for example. Okay, and you can continue to use the models. Okay, but from time to time you may need to retrain your models. Okay, because we know that over time the trend may change. Okay, the trend may change. So that's why you may need to have some um some automation, some automated uh updatings or the models updatings mechanisms, so that the model will keep learning. Okay, we keep learning so that you don't have to retrain and retrain, redesign, and do everything again and again. Okay, so yeah, these are very briefly about the pro and cons of the ARIMA models. So some homeworks that I want you to do is I want you to look at some engineering related case study. Okay, that is using ARIMA or using some variations of ARIMA, for example, the SARIMA SA, the seasonal one, or the vector-based, okay, or some other models, okay? And then from there, you may be able to see the weaknesses or the limitation of the ARIMA models, and you will learn some more advanced methods used in time series predictions. Okay, yeah, so that will be some homeworks, that additional readings that you can read. Of course, like I say, this kind of reading you do not need to read in deep, go and solve all the equations and or learn their Python code on how to do it. No, you just have to read and then understand the basic concept. Okay, and then maybe you can evaluate yourself. Is it better? Is it not as good? And so on. Do some thinking. Okay, do some thinking analysis and so on. Okay, yeah. And again, don't forget to look at the code. Okay, look at the code also. I think you will spend about 10 minutes only. Just run the code and see the output. Okay, 10 to 15 minutes. Okay, so just to run the code and see the output. Yeah. So yeah, I think that's all for this week number 10 lecture. So it's just nice 2 hours. Okay, so yeah, I think I will not do any Q&A. So if you have any questions, I believe you can contact me, or you can wait until we have physical classes, then we can discuss together. Okay, so yeah, so I think that's all for today. Okay, so thank you so much.